Okay, so this evening we're starting our second unit, which is chapters 3 and 4 in the textbook. And what we were looking at last week, we talked about bar graphs and pie graphs. And that's displays for categorical data. And one thing that we need to talk about there yet is what if we have, oops, somebody commented there. Okay, we're still good. What if we just have raw data and we need to organize it somehow? Well, if I just give you a set of responses to a question, if we ask people what is their favorite color, and give them the choice between red, blue, and green. And here's our list of responses that we get, just by first letter. So I just did R, B, and G. Well, looking at that list, it's really tough to decide what is the most common color. If I was looking down here, I would say I see a lot of red, so I might say red is the most popular color amongst that group. But if I'm looking in here, I see a lot of blue, so I might be tempted to say blue is the most popular color. Or if I'm looking down here, I see a lot of green. There's a lot of human psychology and statistics. And one thing in human psychology is that we can only really comprehend between 7 and 13 things at a time before things start to blur out around the edges. So as I'm looking at this data set, I'm probably not even seeing everything in that circle, but I'm definitely not seeing more than that as I'm focusing on a piece of that data set. So in order to make sure that we have an accurate view of the data, we can organize it some. So we're going to use a frequency table. In our frequency table, we have the color, and then we're going to list the frequency. Now, in order to get the frequency, I am going to add another column at the end here called tally. Now, this would not be part of my frequency table when I was done. It's a working column that I use to help to tally up the data, to be blunt. So let's take a look here. I'm going to go to the right color here. As we go through our data, I'm just going to read them off and tally them up. I got red, green, red, oops. Here we go. Red, green, red, red, blue. Red, green, red, red, blue. Green, red, 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 blue. Green, red, 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 blue. Red, green, red, blue, red. So red, green, red, blue, red. And we keep going. Green, blue, 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 red. Green, blue, 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 red. Blue, green, blue, blue, red. Blue, green, blue, blue, red. Blue, blue, green, red, green. Blue, blue, green, red, green. Green, blue, green, green, green. Green, blue, green, green, green. Red, blue, green, green, green. So red, blue, green, green, green. So what we have for frequencies, there's 40 responses there. We have 13 red, 13 blue, and 14 green. Would not have probably guessed that they would be that close by looking at those responses. And of course, then this data could be taken to the next step by doing either the histogram, or not the histogram, the bar graph or the pie graph from that data once we made that frequency table. Well, tonight we want to look at organizing numerical data. And we'll start out with a similar thing. We're going to do a frequency histogram or frequency table, but that frequency table is going to be broken down into two types. First is for discrete but small or limited response. Why limited response? What limited response means is there's only a certain small amount of possible responses, so it's possible to list them out. This would look something like this. If we were to ask students how many classes they were taking, we might get a table of responses, something like this. So the most classes anybody that we surveyed took was 6. And we have a total of 200 students surveyed. That's their frequencies. This is limited response because 1, 2, 3, 4, 5, 6, we can list those out. That's not too many. And even if somebody was really taking a heavy load, it wouldn't be more than 7 or 8 classes. If we had asked number of credits taken, that would be a different story. That could have been anywhere from 1 to 19, 20, 21, somewhere in there. That would be too many to list out. That would not be limited response. That would be either a large response discrete, or the same happens with continuous data. Because with continuous, obviously, no two data points are exactly alike unless they fit our chosen rounding. And with a large response, like number of credits being taken, well, it's possible there's way too many to list them out individually. So we would group them. So it might look something like this. This here table is looking at the length of parts coming off a machine that's set to produce them at exactly 12 inches, or 12 centimeters, I should say. And so coming off, they're not exactly 12 centimeters. Some are a little bit shorter, some are a little bit longer, but they're close to 12 centimeters. So you can see here they're grouped. It's not just 11.8 centimeters, it's 11.80 to 11.90. How many are in that range? Because we can't possibly list all of the different possible lengths. From those, we can create a histogram. A histogram is very similar to a bar graph with a couple of big differences. The first big difference is, of course, that along the bottom, we're not going to have categories anymore. We're going to have numbers. So here we might have our classes. And of course, over here is going to be frequency still. So for the number of classes, let's see, we need to go up to, looks like 70, we need to go up to 80. So I'm just going to number by 20s here. And when I make my bars, just like with the bar graph, I want to try to make sure my bars are the same width. So one class, there's only 12 people that had only one class. It'd be something like that. 2 classes were 32, so it'd be somewhere in there. 3 classes was 76, so that's going to be somewhere up in there. 4 classes is 58. So like that. Trying not to overlap them, I'm trying to get them tight together at the same time. 5 is 16, and 6 is 6. You'll notice, I didn't get them spaced real well, but you'll notice that there's no space between the bars here at all. That's because it's numerical data. When we were talking about favorite color, we'd put space between them on the bar graph because there's no logical order from one to the next or flow from one to the next. We could put those colors in any order and it would make sense. The numbers, there is a logical order, 1, 2, 3, 4, 5, 6, and it does flow. 2 comes after 1 and 3 comes after 2. So we put the bars tight together, again, for that psychological effect of you see the bars connected, so your mind knows that that data is connected from one to the next. Just a little bit of an accuracy of display. Well, our next thing then is, rather than summarizing our data graphically, is to summarize it numerically. In order to summarize data numerically, we must talk about data distributions. A data distribution is just that. It's how the data is distributed. Let's look at test scores. So let's say that for a given test, nobody scored below a 60 or above a 100. So we're going to make a number line that is numbered from 60 to 100. And we're going to put dots on here for the scores. Let's say our first student scores 79. So put a dot above 79 to represent their score. Second student's an 85. So put a dot there. Maybe a 74. Another 79. So we stack, there's already a dot there, so we stack them up. And an 80. 71. And we keep putting these dots on here to represent the scores of our students. I'm not going to put a lot on here just because it's taking a lot of time, but as we put those dots on there, we see a shape develop. And the shape that develops as these dots build up, usually, it doesn't always have to be, but if we were to draw a line through the top of the dots, it's generally going to be a bell curve like that. Well, the technical name for that bell curve is a normal curve or normal distribution. It's called a normal distribution because in nature, that is the shape that data normally takes. If you're looking at the height of people, it would be a normal distribution or approximately normal. The time it takes to perform a task. You're never going to perform it the exact same amount of time every time. It takes a little longer, a little less. Your time is going to fall in a normal distribution like that. So if I have another number line here, and let's do a bell curve here. I want to compare that to that green curve to this blue curve. Now they're about the same width, same height, same everything. The difference between them is, I would say, the center of the green curve is down here and the blue curve is up there. The blue curve is moved over, shifted over to the right, or they have different centers. They're centered at different places. Well, by bringing this purple curve, that purple curve has approximately the same center as the green curve right there. The purple curve is just narrower. It's less spread out. So the two things that we can use to describe these curves is their center and their spread. And the term this textbook uses for spread is variability. So let's look at describing the center and variability for sets of data. Well, I'm going to bring up two sets of data here. My first set of data, which I'm going to label data set A, has 6 items in it. That's where that n equals 6 comes in. That's saying there's 6 items in the data set. My second set, which I'm going to label set B, has 5 items in it. So n is the abbreviation we use to represent the number of items in a set. So let's talk about measures of center. The first one is the mean. The mean is what we've been using since we were in elementary school, called the average. You add them up, so sum of the x's divided by n, divide how many are there. So for set A, well, we would add up, let's see here, we've got 27 plus 19 is 46, plus 23 is 69, plus 33 is 102, plus 29 is 131, plus 25 is 156, divided by, there are 6 of them there, So 156 divided by 6 is 26. The mean of data set A is 26. For data set B, we'll do the same thing. So we've got 17 plus 13 is 30, plus 10 is 40, plus 21 is 61, plus 14 is 75, divided by 5. There's 5 items in that set. So 75 divided by 5 gives us a mean of 15 for set B. So that's one measure of center for each of those sets. So we can say that set A definitely has a larger center than set B. Another measure of center is the median. The median is the middle number in the list. To find the median, we go through a 3-step process. First, we put the numbers in order. Second, we find the location of the median. We do this by taking n, the number of items in the set, times 0.5. Why 0.5? Well, because the median's in the middle, which means half of the numbers are smaller than it. 0.5 is 1/2. So 0.5 or 1/2 times n. And then we identify the median, the number that's in that location. So for set A here, we'll put those in order. Looks like we've got what? 19, 23, 25, 27, 29, and 33. So location of the median. 0.5 times n is 6 for this data set, that's 3. Since this is a whole number, the location is between that and the next number. What does that mean? Well, that gave us a 3. So that means our location is between the 3rd and 4th number in the list. Well, the 3rd number is 25 and the 4th number is 27. So between those, we're just going to add them together and divide by 2. So 25 plus 27 divided by 2 gives us 26 is the median. That's what's between those two numbers. That is the center of the data. Half the numbers are smaller than 26. Half the numbers are larger than 26. Well, because n was even there, we got a whole number when we looked for the location. For set B, put those in order. 10, 13, 14, 17, and 21. Here, when we go to look for the location, n is odd. It's 0.5 times 5 gives us 2.5. Since this is a decimal, we round up to the next spot. So that means that 2.5 rounds up to the 3rd spot. So the number that's in the 3rd spot there is the 14. 14 is the median. Now you'll notice set A had a mean of 26 and a median of 26. The exact same number. That's a pretty good measure of center if we get the same number for different measures. That means that that data is probably, has a good chance of being normally distributed, I should say. Set B, we've got a mean of 15 and a median of 14. They're not exactly the same, but they are close. And they should, all the measures of center should be close to the same. This one may still be approximately normally distributed, but not as close to normally distributed as set A is. In a normally distributed set of data, the mean and median should be the same. Now we have another measure of center, which is called the mode. The mode is the number that occurs the most often. Now you look at both of these data sets, there is no mode. The mode is only useful really if we have large numerical sets. These weren't large, 5 and 6 are not very big sets, or for categorical data. And that's really where the mode plays its biggest roles in the categorical data, because we can't find it. Looking at the favorite color, we can't find the mean or the median of red, green, and blue, but we can find which one occurs the most often. It was green in that set that we just looked at. So let's take a look then at measures of variability. So I'm going to grab my data set from back here again quick. So our first measure of variability is called the range. The range is simply the largest number, which is called the max, minus the smallest number, which is called the min. So for set A, the largest number is 33, minus the smallest number of 19. That gives us a range of 14. For B, the largest number of 21, minus the smallest number of 10 gives us a range of 11. So we do get a difference in range. Set A is more spread out, which makes sense, as more data points in it as well. It's a more spread out set of data. Well, the thing is, looking at set B, I can make a lot of data sets that have 5 data points in them that have the same, mean there was 15. They could have a mean of 15, and they would still have very different ranges, or have the same range but still be more or less spread out, not be the same amount of spread out or variability. So we need something a little more precise than just a range. So what we use is a variance and standard deviation. These are different measures of variability, but they are different steps of the same process. It's a long formula. The difference is the variance is the standard deviation squared. So they are very closely related. For this course, we tend to use the standard deviation. In more advanced methods, non-parametric methods, they would use the variance rather than the standard deviation for a lot of their procedures. There's a formula in the book, which is a pretty ugly formula. I prefer to give it as a 6-step process. Step 1 is to find the mean. We're going to use set A here. The mean was 15. I already found that. Or not set A, sorry, set B. The mean was 15. Second step is to subtract the mean from each number. So we got 17 minus 15 equals 2. 13 minus 15 equals negative 2. 10 minus 15 equals negative 5. 21 minus 15 equals 6. And 14 minus 15 equals negative 1. Those numbers that we just found have a name. They're called the deviations. Sometimes called the deviations from the mean. Well, step 3 is to square the deviations. So 2 squared is 4. Negative 2 squared is 4. 5 squared is 25. 6 squared is 36. And negative 1 squared is 1. Now I want to make a little note here, quick, a side note on the calculator. Oops. Yes, that's exactly it, Evan. Is in the bar graphs, those gaps between the bars are implying psychologically that there isn't a connection from one category to the next, or even a natural order or natural flow. That's why they're separated. Yes, good question. On our calculator, if I have something like negative 5 squared, if I just type in negative 5 squared, it's going to spit out negative 25, which is not the correct answer. We know any number squared has to be positive. So why does that do negative 25? Well, the calculator uses a strict order of operations. It does the squared first, then it applies the negative. So to make sure it does this correctly, we have to put the -5 in parentheses and then squared. That correctly gives us 25 as our result. So you have to be careful with that. So we've squared each of those numbers. Step 4 is to find the sum or the total. Well, we add all those up. We get, oh, what is that? 40, 30, 70 we get for the total there. That's step 4. Step 5 is where people make their mistakes. Step 5 depends on whether it's a population. Now, a population almost never occurs that we have data from a whole population. If it's a population, we would divide by capital N. We use capital N for the size of a population, little n for the size of a sample. If it's a sample, we actually divide by n minus 1. The reason for that is if it's a sample, if we actually know the population parameters, the last item of the sample has to be a predetermined value. It's not free to vary. So it's called degrees of freedom. So we divide by n minus 1 instead of n if it's a sample. Unless we are specifically told it's a population, generally assume that it's a sample. Now, I believe there is one question in the homework where they actually are using a population and they say it's a population. So you have to do that. But here, this is a sample. So this is a sample. So since n equals 5, oops, lost it there. N equals 5, and minus 1 equals 4. So we're going to divide by 4. So we have 70 divided by 4 equals, was that 17.5, I believe. That number right there, by the way, is called the variance. So if you were asked to find the variance, you would stop right there. Step 6 is required for the standard deviation, and that is to find the square root of the variance. So we do the square root of 17.5, which is, I believe, 4.18. That is the standard deviation. What that is saying is that on average, each data point in this set is 4.18 units away from the mean. So it gives us an idea of how spread out our data points are. If we had a longer class period here, I would give you another data set that's obviously more spread out and calculate the standard deviation and show you that that number is larger. You guys have the procedure for calculating, and on your own, I would recommend you do something like that. Take data sets that are more spread out than others and try it. I mean, I'll give you an example here. We might have 5, 10, 15, 20, and 25. That's a data set with a range of 20, a mean of 15. I have another data set, 5, 14, 15, 16, and 25. That still has a range of 20 and a mean of 15, but I would say that the top set is way more spread out. That second set, the points are closer to the middle. I might have 5, 6, 15, 24, and 25. I would say these points are more spread out yet. If you wanted to, you could find the standard deviation of those sets, and you could find that bottom set has the largest standard deviation, where the second set has the smallest standard deviation. So it's an exercise I recommend you try on your own. I'm not going to force you to do it here, just for the sake of time. There is another measure of variability called the interquartile range, abbreviated IQR. But before we can do that, we need to get to where we will find quartiles. So we're going to talk a little bit here about measures of position or location within the data. And the most common one that I'm going to talk about is the percentile. Percentile is the percent of data smaller than a certain number. So I'm going to give you a data set here. It has 20 numbers in it. These are test scores. Now, similar to the median, one of our steps here is going to be to put them in order. So I already put them in order. Step 2 is to find the location. Just like with the median, only it's going to be not 0.5 every time. It's going to be based on a percentile. So I might ask you to find the 65th percentile. Well, the position, it's not 0.5 anymore because it's not halfway, it's 65% of the way. So 65th percentile is 0.65 times n, which is 20 here. That gives us 13. Now again, that's a whole number. So that means it's between that one and the next. So it's between the 13th and 14th number in the list. So let's take a peek here. Let's see, 1, 2, 3, 4, that's the 5th. 3, 4, that's the 10th. 1, 2, 3, 4, 5. There is the 15th. 13th and 14th are both 87. Well, pretty easy to do that. That is 87 is the 65th percentile. If I ask you to find the 23rd percentile. So again, our position or location, 0.23 times n, which is 20, gives us 4.6. This is a decimal, so we round up. So that means it's 4.6 rounds up to the 5th spot in number in the list. Well, the 5th number in the list, if you look up there, is 75. That is our 23rd percentile. Now, only 20 numbers in this list. It sounds like a big list, but it's actually relatively small. 75 is actually the 23rd and the 24th and probably the 21st percentile as well. So it's not a very precise measure here of position. Percentiles, when we have really large sets like 500, 600 points or more, we can really pinpoint those percentiles. Now, the other way we could go is we could ask what number is in, or what percentile is a certain number. That's what percentile is 78. Well, to find the percentile a number is in, it is equal to the number smaller plus 1/2 times the number equal to it, divided by the number in the list, divided by n. So for 78, there are 6 numbers that are smaller, plus 1/2 times, there's only 178, so there's one number equal, divided by n of 20. Well, 1/2 plus 1 is 1/2. So 6 plus 1/2 times 1 is 6.5 or 6.5, divided by 20. Which gives us, what is that, 0.325? So that's the 32.5 percentile. We might ask, what percentile is the 87? We already calculated before that if I was asking for the 65th percentile, we got 87. But calculating the other way, it might come out slightly different. There are 12 that are smaller, plus 1/2 times 2 that are equal, divided by our 20. Well, 1/2 times 2 is 1, so 12 divided by, or 12 plus 1/2 times 2 is 13, divided by 20, equals 0.65. So it is the 65th percentile. So it works out the same backwards. Because it's a small data set, it might be a couple percent off when you go backwards or forwards with that. Well, the percentiles, like I said, are useful for standardized testing. If your child takes a test at school and they say your child's in the 52nd percentile, A lot of parents get upset. That's basic. 50th percentile is in the middle. That's average. 52nd percentile is just slightly above average. So nothing unusual and nothing poor there. If they say they're in the 89th percentile, that means they're better than 89% of the people who took that test. So that's doing pretty well. Let's get a question here. Let's take a look. Nope, even if it was 4.1, we would still round up. Any decimal for position is always rounded up. Because if we round it down to the 4th position, it's not larger than 23% of the data anymore. It's larger than less than 23%. So we always have to round up for position. Very good question. Well, what we want to look at, we said interquartile range implies we need to find quartiles. Quartiles divide the data into 4 equal pieces. By equal pieces, I mean 4 groups that have the equal number of data points in them. If you think about this, if you have an item here and you're going to cut it into 4 equal pieces, it takes 3 cuts. So there are 3 quartiles. We have the lower quartile, or sometimes called the first quartile. It's abbreviated Q1. This is just the 25th percentile. The second quartile is actually the median. It's the 50th percentile. Well, the 50th percentile would be 0.5 times n. That's the location of the median. And then we have the upper quartile, sometimes called the third quartile, abbreviated Q3. That is the 75th percentile. So if we can find percentiles, we can find quartiles. So for our set of data here, let's find the quartiles. Well, Q1 is 0.25 times 20, which equals 5. So it's between 5th and 6th. 5th number here, oops, come here. 5th number is 75, the 6th number is 77. So technically we should do 75 plus 77 divided by 2 gives us 76 is the first quartile. For the second quartile, or the median, it's 0.5 times 20 equals 10. So that means it's between the 10th and 11th numbers in the list. Well, the 10th and the 11th numbers, 83 and 84. Oops, let me get that out of there. One, two, three, four, 5. It is 83 and 84. So we add those together. 83 plus 84 divided by 2 is 83.5. That is the median. And our third quartile, Q3, that's 0.75 times 20 is going to be 15. So that's between the 15th and 16th numbers in the list. That's between 89 or 88 and 90, which is going to be 89, of course. We'll do 88 plus 90 divided by 2 is 89. So that is our third quartile. So what this tells us is actually called a 5-number summary. Let's get back here. Our 5-number summary is made up of obviously 5 numbers. The first is the minimum. The smallest number in the list was a 63. The first quartile was 76. The median was 83.5. The third quartile was 79. Not 79, 89, I should say. And then we have the maximum, the largest number in the list, which was 99. So this 5-number summary can be used to create a box plot, sometimes referred to as a box and whisker plot. To do that, we make a number line again, very similar to our dot plot. So we have to go from 60 it didn't take some of it. Let me try that again. There we go. We got our numbers out. Put a line above it here. And now we're going to plot the minimum and maximum with a dot. So 63 is the minimum. We're going to put a dot above 63 right there. 99 is the maximum. We'll put a dot above 99 right about there. That's the minimum and the maximum. Then we're going to take a box, and our box is going to go from the first quartile to the third quartile, from 76, which is right here, to 89, which is right about there. There's that box. And then the median, the 83.5, is going to get marked with a line in the middle of that box, like that. And then we will make whiskers out to the minimum from the first quartile, and from the third quartile out to the maximum. There's our box and whiskers. This gives us an idea of how spread out the data is, because each section of this graph is 1/4 of the data points. This section here is 1/4 of the data points. That's a fourth, that's a fourth, and that's a fourth. Well, we can see this section is wider than this section by a lot. So that means the data points here are more spread out than they are here. Here they're the tightest together because that's the smallest section of the graph. So this box plot tells us where the data points are packed together and where they're more spread out. And it makes sense that they'd be more spread out on the ends here and tighter together in the middle. That's just how data usually is. It's more towards the center than it is towards the ends. So one of our measures of variability we talked about was the interquartile range, the IQR. And that is found by taking the third quartile minus the first quartile. So here that would be 89 minus 76, which is 13. Well, if we compare that to the overall range of this data, which is 99 minus 63, or 36, there's a lot of comparisons we can be made. If the IQR is exactly half of the range, this is what you would call most likely a uniformly distributed set of data. In other words, it's equally spread out along the whole range of the data. If the IQR is less than half of the range, then it's more in the center. It's possibly a normal distribution, not guaranteed, but to be a normal distribution, it does have to be tighter in the center. So the interquartile range does have to be less than half of the range. And there's a lot of things we can do to compare with that as we're going through. Now we need to talk a little bit about outliers. Outliers are points that fall away from other points. They could either be mistakes, maybe an error in measurement or whatever, or very unusual events, occurrences. In either case, we identify them as being questionable, and then we have to decide whether we include them in the analysis or not. The box plot is one tool that we use for identifying outliers. What we use is 1.5 times the inner quartile range. So here that'd be 1.5 times 13, which is 19.5. We find a lower limit or a lower fence, which is going to be Q1 minus that 1.5 IQR. So the first quartile is 76 minus that 19.5 would be 56.5. Well, there are no numbers in this data set smaller than 56.5. There are no lower outliers. An upper limit would be the third quartile plus the 1.5 IQR. So that third quartile is 79, or not 79, 89, I should say, plus 19.5 equals 109 or 108.5. Well, there are no numbers above that, so no upper outliers. Now, these using the 1.5 are what are called mild outliers. And typically in statistics, that's what we're worried about, is the mild outliers. There are extreme outliers. The extreme outliers would be 3 times the inner quartile range. Extreme outliers are almost always either some sort of error or extremely unusual event. The extreme outliers are pretty much always taken out of the data set and not used. Well, now that we have these measures of center and spread, let's talk about what they're used for. One thing they can be used for is to actually summarize our data using something called the empirical rule. If I take a bell curve, of course, the center of that bell curve is the mean. Let's give you a center and spread here. Let's say we've got a data set that has a mean of 78, a standard deviation of, let's go, 7. So this middle here would be the 78, that mean. Well, we go out from that mean, come on, in steps of 1 standard deviation at a time. So this number here would be the mean minus 1 standard deviation. So that'd be 78 minus 7, or 71. This number here would be the mean minus 2 standard deviations. So 78 minus 2 times 7 would be 14, or 64. Oops, that got overlapped a little too much. Remove that down. And this number here would be the mean minus 3 standard deviations. So that's 78 minus, well, 3 times 7 is 21, or 57. And it's similar going this way. This is the mean plus 1 standard deviation. So 78 plus 7, which is 85. This is the mean plus 2 standard deviations. So 78 plus 14, which would be 92. And this last one here is the mean plus 3 standard deviations. So 78 plus 21, or 99. Well, what good do those do us? Well, we are told, the empirical rule tells us that in a normally distributed set of data, and that's important, it has to be normally distributed for the empirical rule to apply. But we expect to have 68% of the data within one standard deviation of the mean. And we expect to have, within 2 standard deviations of the mean, we expect to have 95% of the data. And within 3 standard deviations of the mean, we expect to have 99.7% of the data. Now we can break that down. Since this is symmetrical, the 68% can be split into 38% on each side. Make this a little bit better. So 34% here, half of the 68, 34% over here. The 95% can be split half each way, so 47.5% on each side. Well, I've got the 34 there already, so this would be 13.5%. And this would be 13.5%. And then, of course, out here, this is going to be 2.35% and 2.35% over here. And on the way outside here is the remaining 0.15%. So what is this good for? Well, those percents are always the same. The numbers change depending on the mean and standard deviation for our data set, but those percents are always the same. So if I ask what percent would we expect to be less than 71? Well, here is 71, less than would be here. If I add those all up, those percents, I get 16%. So my answer there would be 16%. I would expect to be less than 71. Or if I'm asked what percent would we expect to be between 64 and 85. Well, there's the 64 right there. 85 is up there, so it's those percents. We add those up, that's what, 68, 81.5%. That is between those two values. So we can use this empirical rule to do a lot of predicting. If we want to know what is the top 2.5%, well, this is 2.5%. If we add those together, so the top 2.5% would be those above 92. So we can use it backwards like that as well. These percents in here come from the normal distribution. And when we talk about continuous probability distributions, we'll do a lot more with this normal distribution. But for now, just having this approximate empirical rule allows us to do a lot of predicting about the data. Well, that only applied, as we said, if the data is normally distributed. What if it is not normally distributed? Well, for any distribution of data, there's something called Chebyshev's rule. Says that at least a certain percent will be within k standard deviations of the mean. So we start out with k has to be greater than or equal to 2. If it's less than 1, just doesn't work, and if it's less than 1, it definitely doesn't work. Some textbooks say it just has to be greater than 1. Others say it has to be at least 2. So what the rule is the percent, or the minimum percent, it should say, within k standard deviations of the mean is 1 minus 1 divided by k squared. So if we have that mean of 78, standard deviation of 7 again, find the minimum percent between 64 and 92. Well, 64 and 92, if I compare them to the 78, 78 minus 64 is 14. That's 2 standard deviations. 78 minus 92 is a negative 14. That's also 2 standard deviations away. So this is k equals 2. It's 2 standard deviations. So that's 1 minus 1 divided by 2 squared. Well, 1/2 squared is 1/4, or 0.25. 1 minus 0.25 is 0.75. So that's saying at least 75% of the data, even if it's not normally distributed, at least 75% of the data should be between 64 and 92. That's Chebyshev's rule. Applies to any data set, even if it's not normally distributed. Well, similar to our empirical rule, we have a measure of position called a z-score. A z-score is a powerful tool that measures the location of a data point within its own population. So what do I mean? Well, let's see, look at your entrance tests. To get into college, many of you had to take entrance tests. Let's say in math, you scored a 72. In English, let's say you scored 81. Does that mean you're better at English than you are at math? Not necessarily, because the math test might have been harder. So let's say that the mean for the math test was 64, and the mean for the English test was 70. Well, you're still further above the mean on the English test, but that doesn't mean anything. We've got to take into account how spread out the data is. Let's say the standard deviation for the math test is 4. And the standard deviation for the English test is 6. A z-score is the number minus the mean of the data set divided by the standard deviation of that data set. So for math, the z-score is 72 as your score, minus the mean is 64, divided by 4. Well, 72 minus 64 is 8. 8 divided by 4 is 2. You were 2 standard deviations better than the mean. For the English test, your z-score is you had a score of 81 minus the mean of 70 divided by standard deviation is 6. 81 minus 70 is 11. Divided by 6 is 1.833. It's not quite 2 standard deviations above the mean. Telling you that you actually did slightly better on the math test, because that's a slightly higher z-score than the English test. Okay, we're at that point. Let me show you some of our functions in Minitab that we need to know for the week. Let's get back here. And I'm going to pull in some data sets that I've created just to speed things along. The first thing we want to look at is a frequency histogram. So I'm going to pull in some credit scores here. Now again, you'll notice that just says C1, telling us that that's a numerical column of data. For a histogram, we have to deal with numerical data. So we're going to graph, we're going to go down to histogram. And we're just going to choose simple here. Now I could, at this point, I could go through and I could label what my bins are and stuff like that. I'm just going to let Minitab find them himself. So I'm just going to select the credit score. So Minitab is going to group it how it sees fit. Again, I could use data options and I could use that to set whatever bins I want to, but we're going to leave it just generic, whatever Minitab comes up with. And there's our histogram. Now that's pretty blocky. Doesn't look like it's normally distributed. In fact, we could ask Minitab, if we do the with fit, that's going to put a normal curve over the top of it. Oops, what happened there? Cancel. Let's try that again. There we go. And when we do that, we see that the data is nowhere near following that normal curve. This is not a normally distributed set of data. We could, if we wanted to, I'm going to go back to this one here. If I wanted a relative frequency rather than the raw, this is the raw frequency. This is telling me that between 470 to 490, there were 20 people, 20 values. I'll open the graph. I'm going to right click on this axis here and do edit Y scale. I can go to type, and instead of frequency, I can have it show just percent. Minitab does not show the relative as a 0.25 or whatever. It shows it as a percent. So I do that. Now this same bar here is still the let's go to this one. It's still the 470 to, it's 490 to 510. It's 7.9% rather than 20 items like it was before. If I wanted the cumulative frequency, I could right click, edit, go to my type, and I can either do cumulative percent frequency or cumulative raw frequency. I'm going to go to cumulative raw frequency. And down on the bottom here, it says accumulate values across the bins. That's saying to make them cumulative. I click that box, and now they add up as we go. This top one here, of course, is 253. I had 253 total data values in this set. That's pretty close to a straight line going up there, which tells us this is probably uniformly distributed rather than normally distributed. Normally distributed, it'd be pretty low slope here, it'd get steeper and steeper, and then it would get shallower and shallower up there. Well, let's look at a Pareto chart. A Pareto chart is used for showing, in quality control, it's used for showing occurrence of defects. So what we're going to look at here is what major students are and what grade they got in a certain course. So I'm going to go to Stat menu, Quality Tools, and in Quality Tools, it's Pareto chart. So now we need the defects. What are our defects that we're looking at? Well, we're looking at the grade. Our frequencies then are optional. So we're just going to look at our grades here for now. And you can see here, it doesn't put them in order. We would have to go back in and edit what order we want those in. But it gives us the different grades, the frequency of the different grades. And then this line here gives us the cumulative frequency of those different grades. When we do this, there's a sign down here, do not combine. If I click that, hit OK. For this one, it doesn't change. The do not combine, what that is if you have a bunch of really small categories, it'll combine them into one so that it doesn't give you a hugely spread out chart. Well, we talked about box plots tonight. So let's do box plots. Again, we're looking at test scores here for two different classes. I have a class that meets in the morning and a class that meets in the afternoon. Both classes took the same test. To do a box plot, I'm going to go to Graphs, go down to Box Plot here. I'm going to start out with a simple box plot, which is going to have all of my grade data in one. Now I can go through and set my scales again and my labels. I'm okay with just the standard here, so we're just going to hit OK. And there it is. If I want to, I can point at the box. It's going to tell me my quartiles, my median, my IQR. My whiskers here go to 58 and 94. This stops at 58. This data point's obviously below that. The 58 was the star here is an outlier. It says it is 18 is its value. It even tells us what row it's in. It's in row 27, so I could scroll down here and find it in row 27. There it is, that's the 18. We might assume that's either a mistype, a typo, or there's a person that was sick or whatever, a very unusual value for someone to score that low. We could, let's go back here to graphs and box plot. I'm going to do with groups. So what that means is we are going to split them up by morning or afternoon. I'm still going to put grade in as my graph variable, but my groups is going to be their time. So you see now I get two box plots. This is the afternoon and this is the morning. And this is what's called a comparative box plot. Both box plots are on the same axis over here. And I can see how the medians line up. The morning actually has a larger median. Actually has a larger third quartile and a larger first quartile even. Everything seems a little higher. And of course, the maximum is way higher up here. Everything on that morning looks like it's better scores, except for that one outlier way down here. So it's a great way to compare two data sets. I can see that in general, if we took out that one outlier, my morning class scored better than my afternoon class did. Well, what if we just want to describe these statistics? Let's describe these grades here. Well, I could go to Calc, column statistics, and this is going to ask me to pick what statistic I want to learn. Maybe I want the standard deviation. So I'll click my input variable, I'm going to enter grade. I only have two numerical variables out there right now, so the grade is the one I'm going to use. All this is going to tell me is the standard deviation because that's what I selected. That allows me to find one statistic or one descriptor of that data set at once. If I want a bunch of them, I wouldn't use the calc menu, I'd use the stat menu. I go down to stat and then down to basic statistics and then display descriptive statistics. I'll use my grade again and let's click on statistics here and choose which ones I want. The standard error of the means, that's not something we've learned yet, so I'm going to click that off. Standard deviation, yes. Coefficient of variance is with bivariant data, so we don't care about that. Minimum and maximum, sure. Median and quartiles, sure. So let's go OK. So there we have, for grade, we have the mean, standard deviation, the minimum, the quartiles, the median, and the maximum. Well, what if we wanted to separate these by the morning and afternoon classes? So I pick the grade. I'm going to do a variable to separate them with. I'll click the time. That's my morning or afternoon. My statistics should stay the same. They didn't change. Good. So I'll click OK and OK. Now we get the same data set. It's split up. Rather than having all 80 of them at once, you can see here N was 80. There's 80 items in that set. We split the 40 afternoon and 40 morning. The mean is slightly higher in the morning, but higher standard deviation. And we can see here that all the three quartiles are slightly higher. So except for that outlier, the morning looks to have slightly higher numbers. So that is using Minitab to summarize data and to make our graphs. Now, like I said, for our application assignments, if you're better with Excel and you want to use Excel for some of these basic things, how do you change a column in Minitab to accept text input? You don't have to change the column. It will automatically register it as a text. Here. Let's say I'm going to label this. Let's just do class. Notice the second I type a text item here, it automatically changes it to a text column. So Minitab automatically will change the format of the column to a text as soon as you enter text into it. I see some of you do have to go off to the next lecture. We'll see you next week. And the one thing I do have to put up here yet, we've got to finish up, is our meat quiz. So our meat quiz this week, and since we're low on time, we'll just go ahead and do this together rather than letting you try it first and then go over the answers. So for this data set, I want you to find the mean, median, range, and standard deviation. Well, the mean, we're just going to add them all together and divide by it. N equals 5 here. So we're going to add them together. 23 plus 28 plus 27 plus 14 plus 21 divided by 5. What does that add up to? 51, 78, 92, 113 divided by 5, which is 22.6, I believe, is our mean. Our median, we have to put them in order. So 14, 21, 23, 27, and 28. The position, 0.5 times 5 would be 2.5. Which means you round up to the third position. That's going to be 23 is our median. Our range, largest number of 28 minus our smallest number of 14 gives us a range of 14. The standard deviation. Now the standard deviation, I am going to cheat and I am going to use Excel. Let me get my numbers typed in here. Okay, now we'll switch over to Excel. Just for the sake of time, because the mean is, of course, a weird number. Now in Excel, to find the mean, use equals. The command is average. And you highlight the set of data. You don't name the column like you do in Minitab. You got to highlight the data. So it is 22.6. So this is going to equal this number minus 22.6. So we get all of our deviations here. Next, we're going to do our deviation squared. So that equals this number squared. Then we're going to do the sum. Add those all up. We get 125.2. We're going to divide by n minus 1. Now n equals 5. So n minus 1 equals 4. So we're going to get 125.2 divided by 4. Gives us 31.3. That actually would be the variance. Standard deviation then is going to be the square root of that number, which is 5.59. So we get a standard deviation of 5.59. Now let me enter this quick, and I want to talk just a little bit about rounding. Why did I go to 2 decimal places with the standard deviation? Well, for measures of center, the convention is to go 1 decimal place past the data. So all these data go to the nearest 1. So our measures of center would be to the nearest 0.1. So notice my mean was rounded 22.6. For measures of variation, the convention is generally to go 2 decimal places past the data. So again, all this data goes to the nearest ones. 2 decimal places past that would be the nearest 100th. So that's why I rounded that standard deviation to 5.59, is that's 2 decimal places past the data. That should be everything for the week. Does anybody have any questions? Okay, I realized that was kind of a mouthful. There's a lot of information in these first few weeks, so hopefully we get a little bit shorter, closer to our hour as we go on, but I schedule an hour and a half because it does tend to drag on a bit. I'm going to shut off the recording for you.